Hello there, and welcome to Cosmos for Sleep. Tonight, we're delving into the fascinating and expansive realm of the multiverse theory. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy. And let's begin. The multiverse theory suggests that infinite versions of ourselves exist, living out every possible choice we could ever make. Imagine a vast tapestry of realities, stretching far beyond our own familiar universe. Within this grand cosmic design, every single decision you have ever faced, every path not taken, every subtle shift in circumstance might play out in its own distinct reality. This means that for every moment, countless versions of you are experiencing different outcomes, different lives, all unfolding simultaneously across an unimaginable expanse of parallel worlds. It is a concept that quietly expands the very definition of existence, suggesting that the choices we make and those we do not echo through an endless array of possibilities, each one a living, breathing universe. Our perception of reality, often seen as singular and absolute, gently shifts when contemplating the multiverse. This expansive theory suggests that not only do infinite versions of ourselves exist, but each of us is across these myriad realities. Imagine for a moment that every crossroad in your life, every subtle decision, every path taken or left behind, blossoms into a new universe. In one, you chose a certain career. In another, an entirely different one. In one, you met a particular person. In another, that encounter never occurred. This constant unfolding means that a countless number of yous are quietly experiencing every conceivable outcome, creating a vast and intricate web of personal histories, each as real and vibrant as our own. It is a profound thought, suggesting that the tapestry of existence is woven with an infinite number of threads, each representing a unique journey through time and space. Beyond these personal variations, the very fabric of these parallel universes can be fundamentally different from what we perceive. Scientists believe that in some of these countless universes, the fundamental physical constants, those unchanging numbers that govern the laws of nature, could be entirely distinct from our own. Consider the strength of gravity, the precise speed at which light travels through the vacuum of space, or the exact mass of an electron. These are the underlying rules that define how our universe operates, allowing stars to ignite, galaxies to form, and life to emerge. Yet, in another universe, gravity might be subtly weaker, preventing galaxies from clustering, leaving space as a diffuse, unformed expanse. Or perhaps the speed of light could be different, altering the very nature of time and energy. Such variations would lead to cosmic environments almost unrecognizable to us, where the formation of atoms might be impossible or stars might never ignite, resulting in worlds beyond our immediate comprehension. These subtle shifts in the cosmic rulebook underscore the immense diversity that the multiverse could encompass, far beyond mere variations in events. Indeed, the quiet mechanism for this proliferation of realities is often linked to the very choices we experience. Every decision we make, no matter how small or seemingly insignificant, might subtly create a new branching universe where the alternative choice plays out. This isn't a dramatic, explosive event, but a continuous and unhurried process, leading to countless parallel realities that gently diverge from our own. It means that the universe we inhabit is constantly unfurling new branches, like a cosmic tree whose limbs extend into an endless array of possibilities. Each moment of choice, each interaction, each observation, potentially nudges reality into new, distinct pathways. This perspective transforms our understanding of causality, suggesting that every potential outcome of an event finds its expression somewhere within the boundless expanse of the multiverse. Envisioning this grand scale, our universe might be just one small, serene bubble in an infinitely expanding cosmic bubble bath. This image evokes a tranquil, ceaseless process where new universes are constantly forming, gently separating from an underlying, ever-growing metaspace. These bubbles are not empty voids, but complete universes, each with its own laws, its own histories, and its own inhabitants. They drift apart, perhaps never to interact, yet each is a vibrant, self-contained reality. This model, often arising from theories of eternal inflation, paints a picture of creation as an ongoing, almost leisurely process, where the cosmic canvas is perpetually being filled with new and diverse worlds, an endless stream of emergent realities. To ground this expansive idea in a more familiar context, consider a significant event in our planet's distant past. A universe could conceivably exist where the meteor that ended the reign of the dinosaurs never struck, allowing these magnificent creatures to still roam a different Earth. Imagine a world where the vast ancient forests are still traversed by colossal sauropods, and the skies are dominated by pterosaurs, their wings catching the light. Perhaps in this reality, dinosaurs continued their long evolutionary journey, developing new forms, or even, in a truly remarkable twist, evolving a form of intelligence that shaped their world in ways we can only ponder. This vivid example illustrates how even a single altered historical event can lead to an entirely different planetary trajectory, creating a rich and varied tapestry of life across the multiverse. The very beginning of our own universe, the Big Bang, might also find a new interpretation within this framework. Scientists propose that the Big Bang, which initiated our universe, might not be a unique event, but a common occurrence in a much larger, overarching multiverse. Instead of being a singular, isolated genesis, it could be one of countless such beginnings, each giving rise to a new cosmic domain. This suggests a grander, more continuous cycle of creation, where the energetic sparks of new universes are always igniting, forming a ceaseless cosmic symphony of births and transformations. Our own cosmic origin, therefore, would be a particular instance within a vast ongoing process, a gentle and recurring phenomenon within the boundless expanse of all realities. Finally, the most profound implication for the existence of parallel universes often emerges directly from the strange and beautiful rules of quantum mechanics. Particularly through its many worlds interpretation, this theory implies that parallel universes are constantly splitting off with every quantum measurement. At the subatomic level, particles exist in a state of probabilities until they are observed. Rather than choosing one outcome and discarding others, the many worlds interpretation suggests that every possible outcome actually happens, each in its own newly formed, distinct universe. When an electron, for example, is measured to be in one position, another universe branches off where it was found in a different position. This constant, imperceptible branching at the fundamental level of reality builds up over time, leading to the macroscopic divergences we imagine, quietly generating an unimaginably vast number of parallel realities, all coexisting and unfolding in a serene, continuous dance of cosmic possibilities. This perspective offers a deeply elegant way to reconcile the probabilistic nature of quantum physics with a deterministic view of reality, where every potential truly finds its expression. The grand tapestry of existence extends far beyond the familiar confines of our own cosmos. As we gaze outward, the observable universe unfolds before us, a breathtaking expanse spanning approximately 93 billion light-years across. This immense cosmic vista, filled with countless galaxies and luminous stellar nurseries, represents the farthest reach of light that has had enough time to travel to us since the universe's tranquil inception. Yet, the term observable is key, for it implies a boundary not of physical space itself, but of our current perception. Beyond this cosmic light horizon, it is believed that the universe gently continues, perhaps infinitely. If space truly extends without end, and matter and energy are distributed with a serene uniformity over grand scales, then a remarkable consequence arises. Everything that is physically possible within our universe's laws must eventually recur. This grand, extended version of our own cosmos is often referred to as a Level 1 multiverse. It suggests that far beyond the reach of our most powerful telescopes, identical versions of our galaxy, our solar system, and even ourselves are quietly existing, playing out their histories, not in a separate dimension, but simply at unimaginably vast distances within the very same overarching universe. This concept encourages a profound shift in perspective, moving from a singular, isolated cosmos to one that is merely a segment of an endlessly repeating, grander whole, an almost infinitesimal fraction of a truly unbounded expanse. Venturing deeper into theoretical realms, some intriguing theories propose that new universes could be hidden within the enigmatic embrace of black holes. These celestial giants, born from the tranquil collapse of massive stars, possess such immense gravitational pull that nothing, not even light, can escape once it crosses their event horizon. Within the heart of each black hole lies a singularity, a point of infinite density. It is here, at these profound cosmic thresholds, that some scientists hypothesize the conditions for birthing new, baby universes might arise. Imagine each black hole not as an end, but as a subtle cosmic nursery, a quiet gateway to a new reality. As matter gently falls into a black hole in our universe, it could, in this theoretical model, contribute to the formation of a distinct, self-contained universe on the other side. These nascent universes would then expand, perhaps with their own unique set of physical laws, completely separate and unobservable from our own. This elegant idea transforms these cosmic behemoths from mere devourers of light into silent architects of new realities, endlessly propagating existence through hidden dimensions. The processes within these profound cosmic depths remain a mystery, yet the concept offers a placid explanation for the continuous creation of new cosmic domains, each unfolding its own destiny in isolation. This continuous creation is further illuminated by the concept of eternal inflation, a theory suggesting that space-time is ceaselessly expanding and stretching, giving rise to new bubble universes without end. Recall the idea of cosmic inflation, a rapid expansion in the very early moments of our universe. Eternal inflation extends this notion, positing that this inflationary process never truly ceases everywhere. Instead, it continues in a vast, underlying metaspace, constantly bubbling with emergent realities. Picture this as an immense tranquil ocean where bubbles of space-time are perpetually forming, gently expanding, and then separating from the frothing cosmic foam. Each of these bubbles represents a distinct universe, detaching from the inflating background to embark on its own unique evolutionary path. This process is not a singular event, but an ongoing, unhurried wellspring of cosmic genesis, ensuring an endless supply of new realities. The quiet persistence of this inflationary mechanism means that the creation of universes is a fundamental, ceaseless aspect of the larger cosmic structure, a constant and serene unfolding of potential. In this expansive cosmic bubble bath, these newly formed bubble universes might occasionally drift close enough to experience a gentle interaction. Scientists believe that these bubble universes might, in rare moments, softly collide, potentially leaving subtle bruises or anomalies in our cosmic microwave background radiation. The cosmic microwave background, often referred to as the afterglow of the Big Bang, is the oldest light we can detect, a faint uniform glow permeating all of space. It holds a delicate record of our universe's earliest moments. Should another universe have once brushed against our own in its infancy, the subtle gravitational or energetic disturbance from this interaction could have left a distinct, almost imperceptible pattern in this ancient light. These bruises would not be violent scars, but rather gentle imprints, like ripples spreading across a calm cosmic pond, offering a rare and precious glimpse into the existence of neighboring realities. Detecting such an anomaly would provide profound indirect evidence for the presence of other universes, a whisper from a distant parallel existence. To further deepen our understanding of these hidden realities, string theory offers an elegant and intricate framework. This theoretical approach proposes the existence of extra spatial dimensions beyond the three familiar ones we perceive: up, down, left, right, forward, backward, along with the dimension of time. These additional dimensions are not vast and open, but are thought to be curled up very tightly, too small for us to detect directly. Within this complex geometry, string theory suggests that our universe itself might be a brane, a membrane-like structure gently floating within a higher dimensional space, often referred to as the bulk. Other universes, also existing as their own branes, could lie parallel to ours in these extra dimensions, potentially very close, yet entirely inaccessible to our current observational methods. Imagine sheets of paper stacked closely together. Each sheet represents a universe, existing side by side but unable to directly interact with its neighbors. This elegant model presents a serene vision of parallel worlds, coexisting in a hidden, multidimensional expanse, each a distinct cosmic canvas woven into a larger, unseen reality. The implications of string theory extend further, leading to the concept of the cosmic landscape. This landscape, within string theory, implies an enormous, almost incomprehensible number of possible universes, each with its own unique set of physical laws. If our universe is indeed a brane, then the way that brane is structured and the way the extra dimensions are curled up determines the fundamental constants and laws of physics within that particular universe. The cosmic landscape refers to the vast array of possibilities for how these extra dimensions can be configured, leading to an incredibly diverse set of potential universes. Each point or valley in this metaphorical landscape represents a distinct universe, complete with its own unique set of physical rules, from the strength of electromagnetic forces to the types of particles that can exist. This suggests that the laws governing our cosmos are not unique, but merely one gentle variation among an almost endless ensemble of possibilities. The sheer number of these potential realities underscores the boundless creativity of the cosmos, hinting at a diversity of existence that is truly beyond our immediate grasp. Finally, one of the most compelling arguments for the existence of a multiverse arises from what is known as the fine-tuning problem. This observation highlights the astonishing precision with which our universe's fundamental constants are perfectly aligned for life to exist. Consider the exact values of forces like gravity or the weak nuclear force, or the precise masses of fundamental particles. If any of these values were even slightly different, a mere fraction of a percent in some cases, the universe would be profoundly altered. Stars might never form, or if they did, they might burn out too quickly to produce heavy elements. Atoms might not be stable, preventing the formation of complex molecules. In essence, life as we know it, and indeed any form of complex structure, would be impossible. Our universe appears to be exquisitely fine-tuned for our existence. The multiverse theory offers a serene and elegant solution to this apparent cosmic coincidence. If an enormous or even infinite number of universes exist, each with varying physical laws and constants, then it is statistically inevitable that at least one of them would possess the precise conditions necessary for life to emerge. Our existence, then, is not a miraculous improbability, but a natural consequence of residing in one of the many universes where such an outcome is possible. It shifts the question from, why is our universe so perfect, to, in which of the many universes could we possibly exist, offering a calm, probabilistic explanation for our fortunate cosmic home. As we contemplate the profound depths of the multiverse, our imagination stretches to encompass realities that diverge dramatically from our familiar cosmic home. Among these countless possibilities, some universes might be entirely devoid of stars or galaxies, existing instead as vast, cold expanses of diffuse gas without any luminous structures. Picture an eternal, hushed twilight where the fundamental forces of nature, perhaps too weak to pull matter together, or nuclear reactions unable to ignite, never allowed the birth of the first stars. In such a universe, there would be no brilliant nebulae, no swirling spiral arms of galaxies, no planets bathed in the warmth of a sun. Only a thinly spread, almost imperceptible haze of hydrogen and helium, drifting slowly through an endless, silent void. This tranquil yet barren landscape would lack the vibrant energy and complex chemistry that defines our own cosmos, remaining forever in a state of pristine, unlit simplicity, a testament to the myriad ways existence can unfold. It is a profound thought, to imagine a reality so utterly different, so utterly quiet, without the comforting glow of distant suns. Further extending this gentle exploration of cosmic diversity, we consider that time itself might flow differently in other universes. In our reality, time moves forward with an unyielding progression from past to future, a constant measured tick of the cosmic clock. Yet, in another universe, this fundamental arrow of time could be reversed, perhaps even running backward or exhibiting a non-linear progression. Imagine a universe where events unfold in reverse order, where broken objects spontaneously reassemble and light coalesces back into its source. This concept, while deeply challenging to our intuition, suggests a reality where the very concept of cause and effect might be subtly inverted, leading to a strange yet serene dance of cosmic processes. Alternatively, time might not follow a straight line at all, but rather loop, branch, or jump, creating a mosaic of moments where the past, present, and future intertwine in unexpected ways. Such a universe would offer a deeply tranquil, almost meditative experience of temporality, vastly different from our own linear journey through existence, quietly redefining the very rhythm of cosmic unfolding. The building blocks of existence itself could also vary profoundly across the multiverse. Universes could exist where the fundamental particles that make up matter are entirely distinct from the protons, neutrons, and electrons we know. Our universe is composed of a specific set of elementary particles, each with precise masses, charges, and spins, which combine to form the stable atoms that make up everything around us. But what if, in a parallel reality, these particles had different properties? Imagine a universe where electrons are far heavier, or where quarks combine in unfamiliar ways, leading to entirely new types of stable or unstable atoms. Such a cosmic environment might give rise to exotic forms of matter, substances with properties we cannot even conceive, or perhaps no stable matter at all, just a fleeting dance of ephemeral particles. This profound variation in the very constituents of reality highlights the boundless creativity of the multiverse, where the elementary ingredients of existence are subject to diverse cosmic recipes, leading to an almost infinite array of material manifestations, each silently adhering to its own unique set of rules. Returning to the remarkable observation that our universe appears exquisitely tailored for life, the anthropic principle offers a calm and insightful perspective. This principle suggests that we observe our universe as it is precisely because only such a universe could support observers like us. It is not that the universe was designed for us, but rather that our very existence acts as a filter. If the fundamental constants and conditions of a universe were even slightly different, if gravity were a touch stronger, or the cosmological constant a fraction larger, then stars, galaxies, and planets would likely never form, or complex chemistry would be impossible. In such alternative realities, there would be no conscious beings to observe anything at all. Therefore, the fact that we find ourselves in a universe perfectly suited for life is not a cosmic coincidence, but a gentle act of self-selection. We are simply in one of the fortunate universes where the conditions allow for our emergence, a tranquil explanation for the apparent precision of our cosmic home within the vast ensemble of possibilities. Further expanding our contemplation of reality's nature, the simulation hypothesis posits that our universe, along with potentially many others, could be a complex computer simulation within a larger, more fundamental reality. This elegant idea suggests that an advanced civilization existing in a base reality with computational capabilities far beyond our comprehension might have chosen to create detailed simulations of universes. These simulations would be so sophisticated that the inhabitants within them would be entirely unaware of their simulated nature. Our laws of physics, the vastness of space, and the flow of time would all be meticulously programmed parameters within this cosmic computation. This concept offers a serene and intriguing explanation for many cosmic puzzles, from the fine-tuning of constants to the limits of our observable universe, suggesting that what we perceive as ultimate reality is merely a meticulously rendered environment within a grander, unseen system. It encourages a gentle questioning of our assumptions about existence, inviting us to consider the layers of reality that might lie beyond our immediate perception. Finally, the concept of a cyclic multiverse suggests a serene and eternal rhythm to cosmic existence, where universes repeatedly undergo a big crunch, followed by a big bounce, endlessly creating new cosmic cycles. Instead of a single Big Bang, followed by an indefinite expansion, this theory envisions a universe that, after expanding for billions of years, gently begins to contract under its own gravity, gradually collapsing back into an unimaginably dense state, a big crunch. However, instead of ending in a singularity, this collapse then transitions into a big bounce, a moment of cosmic rebirth where a new expansion phase begins, giving rise to a new universe. This rhythmic dance of expansion and contraction creates an endless succession of universes, each emerging from the ashes of the last, perhaps with subtly different physical laws and initial conditions. It is a vision of cosmic renewal, a tranquil and ceaseless cycle of creation and recreation, where the universe is not a singular event, but an eternal, self-sustaining process, constantly reinventing itself in a timeless cosmic ballet. This unending ebb and flow of cosmic existence paints a picture of profound resilience and infinite possibilities. The grand, sweeping concept of the multiverse, while seemingly a product of modern science fiction, has deep roots in theoretical physics, nurtured by the insights of pioneering thinkers. The very term multiverse was notably popularized by physicist Hugh Everett III, whose groundbreaking many-worlds interpretation of quantum mechanics in the late 1950s quietly revolutionized our understanding of reality. Everett's elegant solution to the perplexing nature of quantum measurement suggested that instead of a single outcome manifesting, all possible outcomes actually occur, each in its own distinct, parallel universe. This radical yet serene idea provided a powerful, deterministic framework for quantum phenomena, moving the concept of multiple realities from the realm of speculation into a serious scientific discussion, gently expanding the boundaries of what was considered possible. His work laid a profound foundation for much of the subsequent exploration into the vastness of cosmic possibilities. It is important to understand that the multiverse theory is not a single, unified idea, but rather a collection of distinct and varied hypotheses, each with different mechanisms of creation. These models, while all pointing to the existence of multiple universes, emerge from different branches of physics and offer unique perspectives on how these realities might be generated and structured. Some arise from the implications of infinite space, others from the dynamics of cosmic inflation, and still others from the fundamental nature of quantum processes or the abstract beauty of mathematics. This rich diversity of thought allows for a comprehensive exploration of cosmic possibilities, each hypothesis contributing its own gentle thread to the intricate tapestry of multiversal theory. Instead of a monolithic concept, it is a mosaic of ideas, each illuminating a different facet of potential existence. One of the most straightforward and perhaps least dramatic forms of the multiverse is the Level 1 multiverse. This concept is a direct consequence of an infinite, spatially flat universe. If our universe truly extends without end, and its matter and energy are distributed uniformly on the largest scales, then the laws of probability dictate that everything that can possibly happen given our universe's physical laws, must eventually happen an infinite number of times. This implies that far beyond our observable cosmic horizon, there are regions of space where cosmic events, stellar formations, and even entire histories are precisely repeating themselves. You, reading this, have countless identical copies living out identical lives in distant, unreachable corners of this vast, singular universe. It's not about separate dimensions, but simply about an expanse so immense that all possibilities are statistically realized, creating an endless, tranquil recurrence of events within the same overarching reality. Moving to a more dynamic form, the Level 2 multiverse describes bubble universes, or pocket universes, which arise from the continuous process of eternal inflation. As we explored earlier, eternal inflation suggests that the rapid expansion of space, which gave birth to our own cosmos, never truly ceases everywhere. Instead, different regions of this inflating metaspace expand at varying rates, causing new, distinct bubbles of spacetime to nucleate and gently detach. Each of these bubbles then evolves into its own complete universe, often with its own unique set of fundamental physical constants and laws. Imagine an endless, frothing cosmic ocean, perpetually producing new, self-contained bubbles that drift apart, forever separated by the ceaseless expansion of the space between them. This model presents a serene and ongoing process of cosmic creation, a continuous birthing of distinct realities, each unfolding its own destiny in quiet isolation. The Level 3 multiverse is synonymous with the many worlds interpretation, which we touched upon previously. This interpretation posits that every quantum measurement causes the universe to split into multiple realities. When a quantum event occurs, instead of collapsing into a single outcome, the universe gently branches, creating a new parallel reality for each possible result. This means that every time a particle's position is measured or an atom decays, the universe quietly bifurcates, leading to an ever-multiplying forest of parallel realities. In one branch, the particle is here. In another, it is there. In one branch, the atom decayed. In another, it did not. This constant, subtle branching is happening all the time, at every quantum level, ensuring that every potentiality finds its expression in some corner of this vast, interconnected cosmic tree. It is a deeply elegant and deterministic view of quantum mechanics, where all possibilities are realized in a serene, continuous unfolding of existence. Perhaps the most abstract and expansive of these classifications is the Level 4 multiverse, proposed by the esteemed cosmologist Max Tegmark. This profound concept suggests that every consistent mathematical structure corresponds to a real, existing universe. Tegmark posits that our physical reality is ultimately a mathematical structure, and if so, then any other mathematical structure that is logically consistent must also correspond to a real, existing universe. This implies that not only do universes exist with different physical constants or initial conditions, but also universes governed by entirely different fundamental laws, perhaps even laws that we cannot yet conceive. It challenges the very distinction between abstract mathematical existence and concrete physical existence, suggesting they are one and the same. This ultimate level of multiverse is a testament to the boundless elegance of mathematics, proposing that every logically coherent cosmic symphony is playing out somewhere in the serene, infinite expanse of reality. Among the brilliant minds who have shaped our understanding of the multiverse, André Linde stands as a prominent theoretical physicist and a key proponent and developer of the eternal inflation model. His work has been instrumental in demonstrating how this continuous inflationary process naturally leads to a Level 2 multiverse. Linde's contributions have provided robust mathematical frameworks and compelling arguments for the idea that our universe is just one of many bubble universes that have nucleated and expanded from an eternally inflating background. His serene and persistent exploration of these concepts has helped to solidify eternal inflation as a leading candidate for a multiverse mechanism, offering a profound and elegant explanation for the vast diversity and constant creation of realities. Linda's insights continue to guide much of the contemporary research in cosmology, gently pushing the boundaries of our cosmic understanding and opening new pathways for contemplating the true scale of existence. The most profound and widely discussed engine for the creation of multiple universes lies within the elegant framework of inflationary cosmology. Cosmic inflation, a period of extremely rapid exponential expansion that occurred just a tiny fraction of a second after the Big Bang, is a crucial mechanism for generating level 2 multiverses. Imagine the universe, in its infancy, expanding at an unimaginable speed, far exceeding the speed of light, not by matter moving through space, but by space itself stretching and growing. This brief, powerful surge smoothed out irregularities, made the universe remarkably uniform on large scales, and stretched tiny quantum fluctuations into the seeds of galaxies we observe today. It is this very process, this gentle yet colossal cosmic stretch, that lays the groundwork for the birth of an endless array of parallel realities, setting the stage for a grander cosmic narrative than we once conceived. The concept then extends into what is known as eternal inflation, where the rapid expansion of space never truly ceases everywhere, continually giving rise to new, distinct bubble universes in different regions. Picture a vast, underlying metaspace that is perpetually inflating, like a limitless ocean constantly churning. Within this eternally expanding backdrop, some regions might gently slow down their inflation, allowing matter and energy to settle and form a universe like our own. However, other regions of this metaspace continue to inflate, producing new bubbles of space-time in a ceaseless, unhurried rhythm. This means that the creation of universes is not a single, isolated event, but a continuous and ongoing process, a serene cosmic factory operating across an infinite expanse. The boundless nature of eternal inflation ensures that the cosmos is a vibrant, ever-renewing source of new realities, each quietly emerging from the depths of an expanding void. These new universes, born from the ceaseless process of eternal inflation, nucleate or bud off from the inflating background space, much like bubbles forming and separating in a pot of gently boiling water. Imagine the cosmic foam of the eternally inflating metaspace, where localized pockets of expansion gradually slow, cool, and detach. Each of these detached pockets then becomes a distinct, self-contained universe, embarking on its own unique journey of cosmic evolution. The process is a serene and natural consequence of the dynamics of inflation, a quiet separation that allows for the independent development of countless realities. These bubbles, once formed, expand and evolve in their own right, creating their own galaxies, stars, and perhaps even forms of life, entirely unaware of their origins within the larger inflationary sea. This gentle budding process underscores the organic and continuous nature of universe creation, a fundamental aspect of the multiversal tapestry. A fascinating implication of this bubble universe model is that each of these newly formed realities might possess its own unique set of initial conditions and even entirely different fundamental physical laws. While our universe is governed by specific constants, the strength of gravity, the charge of an electron, the speed of light, a neighboring bubble universe might have different values for these parameters. Gravity could be stronger or weaker, altering the formation of stars and galaxies. The elementary particles themselves might have different masses or interactions, leading to entirely new forms of matter and chemistry. Some universes might be cold and empty, their forces too weak to coalesce matter. Others might be too hot and dense, preventing any stable structures from forming. This immense diversity of cosmic rules means that the multiverse is not just a collection of slightly different histories, but an ensemble of fundamentally distinct realities, each a unique expression of cosmic possibility, unfolding in its own serene and silent way. A critical characteristic of these bubble universes is the immense distances between them, leading to a state where these causally disconnected realities mean that light or information from one cannot reach another. The continuous, rapid expansion of the space between these nascent universes stretches the fabric of space-time so profoundly that they are effectively isolated. Even if a signal were emitted from a neighboring bubble universe at the very moment of its birth, the expansion of space would carry it away faster than light could ever travel, ensuring that it would never reach our cosmic shores. This causal disconnection implies that while these other universes might exist in abundance, they remain forever beyond our direct observation, hidden in the depths of an expanding void. This serene isolation ensures that each universe can evolve independently, without interference or exchange of information, preserving its unique character within the vast, tranquil expanse of the multiverse. The driving force behind this ceaseless expansion and the creation of new universes is theorized to be a hypothetical energy field, known as the inflaton field. In the early moments of our universe, this field is thought to have permeated all of space, possessing a unique property that caused space itself to expand exponentially. As the inflaton field gently rolled down its energy potential, it drove the rapid inflation, eventually settling into a lower energy state that gave rise to the matter and energy we observe today. However, in the context of eternal inflation, some regions of the inflaton field never fully roll down or settle. Instead, they remain in a high energy state, perpetually driving the expansion of space and continuously spawning new bubble universes. This theoretical field acts as the quiet, persistent engine of cosmic creation, its subtle energy fluctuations birthing new realities in an unceasing, majestic rhythm. It is the unseen hand that orchestrates the grand, continuous unfolding of the multiverse. As scientists delve deeper into the intricate possibilities of these alternate realities, a contemporary area of research within string theory, known as the Swampland program, explores which theoretical universes are actually mathematically and physically possible. String theory, with its vast cosmic landscape of potential universes, offers an almost infinite number of consistent mathematical descriptions for different realities. However, the Swampland program seeks to identify which of these theoretically consistent universes are truly viable, distinguishing them from those that are merely mathematical curiosities but cannot physically exist. It acts like a filter, gently sifting through the boundless possibilities to discern the genuine cosmic landscapes from the swampland of impossible realities. By understanding the underlying constraints and consistency conditions, researchers aim to narrow down the immense number of theoretical universes to those that could genuinely manifest, quietly refining our understanding of the fundamental rules that govern the existence of all possible cosmos. This diligent exploration helps to bring a serene order to the vast, complex realm of multiversal possibilities. Among the many theoretical paths leading to the concept of a multiverse, one of the most profound and elegant arises from the enigmatic heart of quantum mechanics itself. This is the many worlds interpretation, or MWI, which offers a serene yet radical solution to some of the deepest puzzles in physics. At its core, MWI eliminates the concept of quantum collapse by suggesting that all possible outcomes of a quantum event actually occur, each in a different universe. In traditional quantum mechanics, when a particle is observed, its wave function, which describes all its potential states, is said to collapse into a single, definite state. MWI gracefully sidesteps this mysterious collapse by proposing a simpler, more expansive reality. Every potential outcome, rather than being discarded, simply manifests in its own unique, parallel universe. This profound shift in understanding allows for a seamless, continuous evolution of quantum states, removing the need for an arbitrary moment of observation to define reality. It suggests that the universe, in its quiet unfolding, always explores every avenue, every possibility, ensuring that no potential outcome is ever truly lost. In this expansive view, the universe doesn't choose a single path. Instead, it branches into new, distinct realities with every single quantum measurement. Imagine a delicate, shimmering fabric of existence. Each time a quantum event occurs, whether it's an electron shifting its energy level, an atom decaying, or even a photon interacting with a detector, this fabric gently divides, creating new, parallel versions of reality. In one branch, the electron settled into one energy state. In another, it settled into a different one. In one branch, the atom decayed at a specific moment. In another, it waited a fraction longer. This constant, unhurried branching ensures that every conceivable outcome of every quantum interaction finds its expression in some corner of the multiverse. It is a continuous, subtle process, a quiet proliferation of worlds, each diverging from its predecessors by the most minute of quantum distinctions, yet collectively building an overwhelmingly vast cosmic tapestry. This constant branching creates an incredibly dense and ever-multiplying forest of parallel universes, each representing a different history. Picture a tree with an infinite number of limbs, each limb adorned with countless leaves. Every leaf is a universe, and every branch point is a quantum event where reality subtly split. As moments pass and quantum events accumulate, this forest grows exponentially, generating an unimaginable number of distinct realities. In one universe, a coin landed heads. In another, tails. In one, a distant star exploded. In another, it continued to shine. Each of these universes, though perhaps only slightly different, is a complete, self-contained reality, evolving its own unique story. This forest is not static. It is perpetually growing, constantly unfurling new branches with every passing instant. A serene testament to the boundless possibilities inherent in the quantum realm. Within this vast, branching structure, observer consciousness is theorized to be tied to a specific branch, experiencing only one of the many possible outcomes. You, as an observer, are not witnessing all the parallel universes simultaneously. Instead, your consciousness, your unique stream of experiences, is effectively located within one particular branch of this cosmic tree. When a quantum event occurs and the universe branches, your consciousness also branches, with one version of you following one path and another version following another. This means that while there are countless versions of you existing across the multiverse, each is experiencing a distinct reality, unaware of the others. It is a deeply personal aspect of the many worlds interpretation, suggesting that our individual experiences are but one gentle trajectory through an infinite sea of possibilities, a single, coherent narrative woven from the vast tapestry of parallel lives. A significant strength of MWI is that it offers a deterministic view of quantum mechanics, gracefully avoiding the problematic probabilistic outcomes often associated with a single universe's interpretation. In traditional quantum mechanics, before a measurement, a particle's state is described by probabilities. It's uncertain until observed. This randomness has long puzzled physicists. MWI resolves this by stating that there is no true randomness. Instead, every probable outcome simply becomes a definite outcome in its own universe. So, while our particular branch might experience one specific outcome, all other outcomes are equally real in their respective branches. This means that the universe as a whole is perfectly deterministic, with nothing left to chance. Every possibility inherent in the quantum wave function is realized somewhere, ensuring a serene and complete unfolding of all potentials, without any mysterious collapse or arbitrary selection of a single reality. To understand how these quantum states separate into distinct, non-interacting classical realities within MWI, the process of decoherence is key. Decoherence explains how the quantum fuzziness and superposition of states, which are so prevalent at the microscopic level, give rise to the clear classical world we experience. When a quantum system interacts with its environment, even with a single stray photon, its quantum information becomes entangled with that environment. This entanglement effectively spreads the quantum state, making it impossible for the original system to revert to its pure quantum superposition. Within the many worlds framework, decoherence is the mechanism that ensures the distinct branches of the universe become effectively separate and non-interacting. It's a gentle, natural process that solidifies the boundaries between parallel realities, allowing each branch to evolve independently and coherently, creating the illusion of a single classical reality for the observer within that branch. Despite its elegant solutions to quantum puzzles, critics of MWI often raise concerns about the unobservable nature and the seemingly infinite number of these branching universes, questioning its falsifiability. Since these parallel universes are causally disconnected and cannot be directly observed or interacted with, some argue that the theory lacks empirical testability, which is a cornerstone of scientific inquiry. The idea of an infinite number of universes, each splitting off with every quantum event, can also seem extravagant and difficult to accept without direct evidence. While proponents argue that MWI is the most straightforward interpretation of quantum mechanics' mathematical formalism, the lack of direct observational proof remains a point of gentle contention. This ongoing discussion highlights the profound philosophical and scientific challenges posed by the multiverse concept, inviting us to contemplate the limits of our perception and the nature of proof in the realm of the truly immense and unseen. Beyond the realms of infinite repetitions and quantum branching, another fascinating pathway to the multiverse emerges from the intricate depths of string theory, the concept of brain cosmology. This elegant idea suggests that our entire universe is. Imagine our familiar three spatial dimensions, up, down, left, right, forward, and backward, as being confined to the surface of an impossibly vast cosmic membrane. This membrane, thin beyond comprehension, is our universe, containing all the stars, galaxies, and matter we observe. This serene and subtle vision redefines our cosmic home not as a boundless volume, but as a bounded surface, a delicate sheet of existence adrift in a larger, unseen expanse. It is a profound shift in perspective, transforming our perception of reality from a three-dimensional solid to a two-dimensional surface embedded within a grander, more complex architecture. Expanding on this concept, other brains, representing other universes, could exist parallel to ours in these extra, unseen dimensions, potentially very close but entirely inaccessible. Picture multiple sheets of paper, stacked closely but not touching, within a much larger room. Each sheet is a universe, a brain, and the room itself represents the higher dimensional space. These parallel brains could be separated by mere microscopic distances in these hidden dimensions. Yet the fundamental forces that govern our everyday lives, electromagnetism, the strong and weak nuclear forces, might be confined to our own brain. This confinement would mean that even if another universe were just a hair's breadth away in an extra dimension, we would remain blissfully unaware of its presence, unable to see, touch, or interact with it. This serene coexistence of multiple realities, so near yet so far, paints a picture of a subtly layered cosmos, where countless worlds might be quietly unfolding their destinies right beside our own. In a truly awe-inspiring extension of brain cosmology, collisions or interactions between these brains could be the true origin of Big Bang-like events, periodically igniting new universes. Instead of a singular event emerging from nothingness, the Big Bang that gave birth to our cosmos might have been the gentle yet powerful impact of two or more brains brushing against each other. Imagine two immense cosmic membranes drifting through the higher dimensional space, slowly approaching. When they finally make contact, the energy released from this gentle collision could manifest as an immense burst of energy and matter, igniting a new universe on one or both of the brains. This cyclical process of cosmic birth, where universes are constantly being reborn through these serene brain interactions, offers an elegant alternative to the traditional Big Bang model. It suggests a universe in continuous motion, where creation is not an isolated event, but an ongoing, rhythmic dance of intersecting realities, perpetually renewing the cosmic tapestry. A particularly intriguing aspect of brane theory lies in its potential to explain one of the great puzzles of physics: why gravity might be the only fundamental force that can leak or propagate between these branes. In our universe, gravity is by far the weakest of the four fundamental forces, astonishingly feeble compared to electromagnetism or the nuclear forces. Brane cosmology offers a serene explanation for this discrepancy. If all other forces are tightly confined to our three-dimensional brane, gravity, by contrast, might be able to extend its influence into the higher dimensional bulk space, subtly diluting its strength as it spreads across these extra dimensions. This means that while electromagnetic forces hold atoms together within our universe, the gravitational pull of a massive object might extend beyond our brane, subtly interacting with other universes. This elegant hypothesis transforms gravity from an anomaly into a cosmic bridge, a gentle, pervasive force that subtly connects all the parallel realities, weaving them into a grander, unseen cosmic web. Central to this entire framework is the existence of bulk space, a higher dimensional realm beyond our familiar three spatial dimensions. This bulk is the expansive stage upon which the branes, our universes, gently float and interact. It is not an empty void, but a complex, unseen geometry, filled with its own subtle properties and dynamics. While our senses and instruments are confined to the surface of our brane, the bulk represents the true, overarching reality in which our universe is embedded. This higher dimensional space is where other branes reside, where they drift, and where their gentle collisions might spark new cosmic beginnings. The concept of the bulk profoundly expands our spatial imagination, inviting us to contemplate a reality far richer and more intricate than our immediate perception allows. It is a serene reminder that what we experience as the totality of existence might be but a small, delicate surface within a much grander, multi-layered cosmic architecture. To rigorously explore these profound concepts, specific theoretical frameworks have been developed. Randall-Sundrum models are specific theoretical frameworks within brane world scenarios that explore these concepts in detail. Proposed by Lisa Randall and Raman Sundrum, these models provide precise mathematical descriptions of how our universe, as a brane, could be embedded in a higher dimensional bulk space. They investigate how gravity's strength might be diluted across these extra dimensions and how the geometry of the bulk itself could influence the properties of our universe. These models offer a serene and elegant way to address the hierarchy problem, the question of why gravity is so much weaker than other fundamental forces. By providing concrete mathematical tools, Randall-Sundrum models allow physicists to test the consistency and implications of brane cosmology, gently guiding our understanding of how our universe fits into a potentially larger, multi-dimensional reality. Finally, the multiverse, in the broader context of string theory, is often referred to as the landscape of possible vacuum states, each representing a different universe. String theory suggests that the universe is made up of tiny, vibrating strings, and the way these strings vibrate determines the fundamental particles and forces we observe. However, string theory does not predict a single, unique vacuum state for the universe, but rather an enormous number of possible stable configurations, each corresponding to a different set of physical laws and constants. This vast array of stable configurations is the cosmic landscape. Each valley in this landscape represents a different universe that could exist. Our universe is simply one particular valley in this immense, serene landscape of possibilities. This concept provides a natural explanation for the fine-tuning problem, suggesting that our life-friendly universe is simply one of the many possibilities realized within this vast cosmic ensemble, a gentle and logical outcome within a boundless field of potential realities. The universe we inhabit, with its luminous stars, swirling galaxies, and the intricate dance of life on Earth, appears to be an exceptionally special place. This remarkable observation leads us to Multiverse, the fine-tuning enigma. The universe's fundamental constants, such as the precise strength of gravity or the delicate mass of an electron, are astonishingly tuned for the existence of life. These constants are not arbitrary numbers. They are the bedrock of physical law, dictating everything from how atoms form to how stars burn. Consider the gravitational constant, which determines the attractive force between objects with mass, or the electromagnetic constant, governing the interaction between charged particles. These values, along with many others, are observed to be set at extraordinarily precise magnitudes, seemingly perfect for the emergence of complexity and consciousness. It's a serene and subtle arrangement, a cosmic symphony played with exquisite precision, allowing for the gentle unfolding of all that we know. The profound significance of this fine-tuning becomes clear when we contemplate the consequences of even minor deviations. Scientists understand that even a slight alteration in these constants would lead to a universe devoid of stars, stable elements, planets, or any form of complex chemistry. Imagine if gravity were just a tiny bit stronger. Stars might collapse too quickly or burn out in a fleeting flash, never allowing enough time for planets to form or for life to evolve. If gravity were slightly weaker, galaxies might never coalesce, leaving the universe as a diffuse, unformed expanse. Similarly, if the mass of the electron were different, chemical bonds might not form, preventing the very existence of stable molecules, the building blocks of everything. In such altered realities, the serene and intricate processes that led to our existence would simply not occur. The cosmos would remain a barren, silent void, incapable of fostering any form of complexity. This delicate balance underscores the extreme sensitivity of our universe's parameters to the conditions necessary for life. It is precisely this apparent cosmic precision that the multiverse theory addresses with a natural and elegant explanation. If countless universes exist, each with its own unique set of fundamental constants, then some are bound to be life-friendly by chance. Think of it like a lottery with an infinite number of tickets. While the odds of winning with any single ticket are astronomically small, if you buy every possible ticket, a win becomes an absolute certainty. Similarly, if there is an immense ensemble of universes, each gently exploring a different set of physical laws, or indeed many, would happen to possess the precise conditions that allow for stars, planets, and eventually, conscious observers like us. Our existence, therefore, is not a miraculous improbability, but a serene and expected outcome within this grand cosmic lottery, a gentle realization of potential across a boundless spectrum of possibilities. Without a multiverse, the extreme fine-tuning of our universe appears as an incredibly improbable cosmic coincidence, raising profound questions. The sheer unlikelihood of all these fundamental constants aligning so perfectly by chance, without any underlying mechanism or explanation, is deeply perplexing to scientists. It would be akin to tossing a coin billions upon billions of times and having it land heads every single time, or finding a single grain of sand on a vast beach that is perfectly shaped in a complex pattern, simply by random chance. Such an improbable occurrence would challenge our understanding of probability and suggest a hidden, perhaps inexplicable bias in the universe's design. The fine-tuning problem in a single universe context often leads to philosophical or theological interpretations, suggesting a purposeful creation. However, the multiverse offers a purely scientific, probabilistic framework, providing a calm and rational alternative to this cosmic riddle. Beyond the fundamental constants of particles and forces, the cosmological constant, which drives the accelerating expansion of dark energy, is another finely tuned value that strongly points towards a multiverse solution. This constant, a measure of the energy density inherent in the vacuum of space, is observed to be incredibly small, yet precisely the right value to allow for the formation of galaxies and stars before the universe expands too rapidly to permit structure formation. If the cosmological constant were just slightly larger, the universe would have expanded so quickly in its infancy that matter would never have had the chance to clump together under gravity, leaving a sparse, empty cosmos. If it were significantly smaller or negative, the universe might have collapsed back in on itself long before life could emerge. Its observed value is so exquisitely precise that it is considered one of the most extreme fine-tuning problems in physics, a subtle cosmic balancing act that seems to whisper of a larger context. The multiverse provides a serene landscape where all possible values for this constant are realized, and we simply find ourselves in one of the universes where it allows for our existence. Furthermore, the initial conditions of the Big Bang itself also appear remarkably finely tuned for the subsequent evolution and complexity of our universe. The early universe was not merely a hot, dense state. It had specific properties, such as its initial smoothness and slight temperature fluctuations, that were absolutely critical for everything that followed. If the universe had been too lumpy or too smooth in its earliest moments, galaxies and stars would either never have formed or would have collapsed into supermassive black holes too quickly. The delicate balance between the initial expansion rate and the initial density of matter was also precisely set. Even a tiny deviation in either direction would have led to a universe that was either too dilute or too dense to support complex structures. This suggests a profound initial precision, a gentle cosmic launch that set our universe on a trajectory toward complexity. The multiverse offers a serene explanation. These precise initial conditions are simply one set among countless possibilities, realized in one of the many universes, allowing for our cosmic story to unfold. Ultimately, the multiverse shifts the why question of our existence from one of cosmic design to one of statistical probability within a vast ensemble of realities. Instead of asking why our particular universe was so perfectly created for us, we ask, given an infinite number of universes, which ones would observers like us naturally inhabit? This reframing changes the nature of the inquiry from seeking a singular purpose to understanding the statistical likelihoods across an immense cosmic backdrop. It suggests that our existence is not a unique, improbable event, but a natural and expected outcome within a boundless field of possibilities. This perspective offers a profound sense of humility and wonder, reminding us that our cosmic home is one delicate facet of an unimaginably rich and diverse collection of realities, each unfolding its own quiet story, a serene testament to the boundless potential of the cosmos. As we gently drift deeper into the concept of multiple realities, it becomes helpful to categorize the various forms the multiverse might take. Cosmologist Max Tegmark has proposed a classification system, and we begin our exploration with the most accessible, yet still profoundly vast idea, the Level 1 multiverse. This level of multiverse is a direct and almost inevitable consequence of an infinite, spatially flat universe that continues far beyond our observable horizon. Our current cosmological models, supported by observations of the cosmic microwave background radiation, suggest that the universe is indeed spatially flat, meaning parallel lines would remain parallel even over cosmic distances, and that it extends far beyond what we can currently see. If this is true, then the universe is not merely vast, but truly boundless, stretching out into an endless expanse, a serene and continuous sea of space-time. This infinite expanse naturally leads to remarkable implications, gently expanding our understanding of what our universe truly means. In such a Level 1 multiverse, if space is truly infinite and matter is distributed evenly across this boundless expanse, then everything possible within our physical laws will eventually repeat infinitely many times. Imagine an infinite canvas upon which all possible arrangements of particles, stars, and galaxies are painted. Given enough space, every combination, every permutation, every cosmic event will not only occur, but will recur an endless number of times. This isn't about different laws of physics, but about the sheer probabilistic certainty within an infinite volume. It suggests that somewhere, at an unimaginably distant remove, the exact sequence of events that led to the formation of our solar system, the evolution of life on Earth, and even this very moment you are experiencing, has already played out or is currently playing out countless times over. It is a tranquil, yet deeply humbling thought to consider that our unique cosmic story is but one of an infinite number of identical tales unfolding across the boundless expanse. This concept leads to a truly mind-bending implication. Your exact copy, an identical version of yourself, could hypothetically be found billions of light years away in such a vast and repeating level 1 multiverse. Not a similar version, but an atom for atom, memory for memory duplicate. The number of possible configurations for particles within a finite volume is enormous, but it is still a finite number. In an infinite universe, every single one of these configurations must eventually repeat. This means that if you were to travel far enough, you would eventually encounter a region of space identical to our own, complete with an Earth, a solar system, and a version of you experiencing this very moment. This is a serene and almost poetic thought, suggesting that individuality, while precious, is not singular in the grand cosmic scheme. It weaves a tapestry where every life, every experience, is echoed endlessly across the silent, boundless stretches of space, a gentle reminder of the immense scale of existence. The mathematical underpinnings for such repetition are found in the concept of recurrence theorem. This theorem, which is central to certain areas of mathematics, supports the idea that states will eventually repeat in sufficiently large or infinite systems. In simple terms, if a system has a finite number of possible states, and it evolves over an infinite amount of time or within an infinite space, it is guaranteed to eventually return to any given state, or at least arbitrarily close to it. Applying this to a level 1 multiverse, where the number of possible arrangements of matter and energy within a finite volume is vast but finite, and the universe itself is infinite, then the recurrence theorem gently implies that all possible configurations, including exact duplicates of our cosmic neighborhood, must eventually manifest. This mathematical certainty provides a serene and logical foundation for the seemingly fantastical idea of cosmic repetition, reinforcing the notion that in an infinite cosmos, all possibilities are realized. Moving beyond the boundless expanse of our own universe, we encounter the next level of complexity, level 2 multiverses. These arise from the process of eternal inflation, where different regions of space expand at varying rates, creating distinct cosmic domains. As we discussed, that initiated our Big Bang never truly ceases everywhere. Instead, different patches of this underlying inflating metaspace can gently slow down their expansion, allowing matter and energy to condense into what we perceive as a universe. Other patches, however, continue to inflate, ceaselessly giving birth to new bubble universes in an ongoing process. This creates a vast, frothing sea of space-time, where an endless stream of new cosmic bubbles are constantly forming and drifting apart, each a distinct and self-contained reality. It is a vision of continuous creation, a serene and perpetual cosmic genesis. A particularly striking feature of these individual pocket universes within a level 2 multiverse is that they can possess vastly different physical laws, constants, and even dimensions. Unlike the level 1 multiverse, where the laws of physics are uniform throughout, the mechanism of eternal inflation allows for much greater diversity. As new bubble universes nucleate and detach from the inflating background, the fundamental parameters that govern their internal physics, such as the strength of gravity, the mass of elementary particles, or even the number of spatial dimensions, can be different. One universe might have a stronger electromagnetic force, another a weaker nuclear force. Some might be 4-dimensional, others 5 or more. This means that these pocket universes are not merely variations on a theme. They are entirely distinct cosmic environments. each unfolding according to its own unique set of rules. This profound diversity offers a serene countless variations that naturally arise within this boundless ensemble of possibilities. Finally, each bubble within a Level 2 multiverse is considered a complete self-contained universe, causally disconnected from its neighbors. Once a bubble universe forms and separates from the eternally inflating background, the rapid expansion of the space between it and other bubbles ensures that no light, no information, and no physical interaction can ever pass from one to another. This means that each universe evolves independently, unaware of the existence of its neighbors, even if they formed just a cosmic hair's breadth away in the underlying metaspace. This causal isolation ensures the distinct identity of each reality, allowing it to follow its own unique trajectory without interference. It is a serene arrangement where countless universes unfold their stories in quiet solitude, each a vibrant, self-sufficient cosmos within the greater, unobservable expanse of the Level 2 multiverse. This gentle separation allows for an immense diversity of cosmic experiences, each a unique expression of the universe's boundless potential. Our journey through the multiverse continues, unveiling even more profound and abstract layers of reality. The Level 3 multiverse, often referred to as the many worlds interpretation, is fundamentally based on the astonishing implications of quantum mechanics and its wave function. Quantum mechanics, the science of the very small, describes particles not as fixed points, but as waves of probability, existing in multiple states simultaneously until observed. The wave function is the mathematical description of these probabilities. In a single universe view, this wave function is said to collapse into a definite state upon measurement, a mysterious process that has long puzzled scientists. However, the many worlds interpretation offers a serene and elegant alternative, suggesting that the wave function never truly collapses, but rather continues its ceaseless, multifaceted existence, quietly unfolding into all possible realities. This profound reinterpretation of quantum physics fundamentally reshapes our understanding of what reality truly is, suggesting an endless, branching cosmic tree where every potential is realized. Indeed, in the many worlds interpretation, the wave function of the universe never truly collapses. Instead, it splits into all possible outcomes for every quantum event, creating new realities. Imagine a single quantum particle with two possible states, perhaps spinning clockwise or counterclockwise. When this particle is observed, MWI posits that the universe gently divides. In one newly formed universe, the particle is measured spinning clockwise, and in the other, it is measured spinning counterclockwise. This is not a choice made by the universe, but a continuous act of proliferation. Every photon that hits an atom, every radioactive decay, every single quantum interaction, no matter how small, becomes a branching point for reality. This constant, unhurried splitting means that the universe is not a singular linear progression, but an ever-expanding, multi-pathed journey, with each quantum event quietly giving birth to new cosmic, serene and beautiful vision of continuous creation, where all potentials are brought into being. Pushing the boundaries of cosmic imagination even further, we arrive at the Level 4 multiverse, a concept proposed by the insightful cosmologist Max Tegmark. This most abstract and encompassing level suggests that every single. Tegmark's radical hypothesis posits that our physical reality is not merely described by mathematics, but is a mathematical structure itself. If this is true, then any other mathematical structure that is self-consistent and logically coherent must also correspond to a real, tangible universe. This means that the universe's existence is not contingent on physical processes like inflation or quantum branching, but on mathematical consistency. Imagine a vast library containing every possible logically consistent mathematical equation. According to this theory, each of those equations represents a universe, quietly existing in its own unique form. It's a profound and serene idea, elevating mathematics from a mere descriptive tool to the fundamental essence of all reality. This implies that any universe that can be described mathematically, regardless of how different its laws, exists as a level 4 multiverse. Consider universes where space has 5 dimensions, or where time flows in multiple directions, or where the very concepts of mass and energy are defined in entirely different ways. As long as these alternative realities can be expressed through consistent mathematical equations, they are considered to be real within the framework of the level 4 multiverse. This level goes far beyond variations in physical constants or initial conditions. It encompasses universes with fundamentally different physics, different geometries, and even different logical structures. It suggests that the laws of our universe are just one particular set of equations, one gentle melody in an infinite cosmic symphony of mathematical possibilities. This boundless scope challenges our deepest intuitions about what reality can be, quietly inviting us to contemplate an existence limited only by the elegance of mathematics. The level 4 multiverse is considered the most abstract and encompassing of Tegmark's classifications, containing all other levels as subsets. This means that if the level 4 multiverse truly exists, then the level 1 multiverse, infinite space, the level 2 multiverse, eternal inflation's bubble universes, and the level 3 multiverse, quantum many worlds, are all naturally contained within its boundless framework. It is the ultimate meta-reality, the overarching structure that encompasses every conceivable form of existence. From the subtle variations of our own physical laws to entirely alien mathematical universes, this hierarchical nesting provides a serene and elegant way to unify different multiversal concepts, placing them within a single, grand, and all-encompassing framework. It suggests that the vast diversity of cosmic realities is but a natural consequence of the boundless creativity of mathematical consistency, a profound and tranquil order underlying all existence. This ultimate level of multiverse fundamentally challenges the traditional distinction between purely mathematical existence and. For centuries, philosophers and scientists have debated whether mathematics is a human invention, a language we use to describe the universe, or if it is a fundamental truth that exists independently of us, forming the very blueprint of reality. The level 4 multiverse leans strongly towards the latter, proposing that mathematical structures are not just abstract concepts, but are inherently real, and that physical reality itself is nothing more than a manifestation of these mathematical patterns. This perspective dissolves the boundary between the abstract and the concrete, offering a serene and unified vision where the universe is a living, breathing equation, and every consistent set of numbers and symbols quietly unfolds into a tangible cosmos. It is a profound redefinition of reality, inviting a meditative contemplation of the universe's deepest nature. Finally, this ultimate level of multiverse implies the existence of universes with entirely different fundamental physics, not just different constants. While level 2 multiverses might vary in the values of their constants, the underlying laws, gravity, electromagnetism, nuclear forces, remain recognizably similar, albeit with different strengths. However, in a level 4 multiverse, the very nature of these laws could be radically different. Imagine a universe where there is no gravity as we understand it, or where the concept of mass does not exist, or where space itself behaves in ways that defy our current geometry. These are not just variations on a theme, but entirely new cosmic compositions, governed by entirely new sets of rules. This boundless diversity means that the level 4 multiverse encompasses the most extreme and imaginative possibilities, a serene and endless repository of all logically consistent cosmic designs, each playing out its unique story in the grand, mathematical symphony of existence. As we gently traverse the conceptual landscapes of the multiverse, a fundamental question naturally arises. How can we ever hope to confirm the existence of these other realities? The challenge is immense, for directly observing other universes is currently deemed impossible. This is primarily because they are either beyond our cosmic light cone or fundamentally causally disconnected from us. For level 1 multiverses, their sheer distance means light from them has not had time to reach us, placing them forever beyond our observable horizon. For level 2 bubble universes, the rapid expansion of space between them ensures that no information, no light, no physical interaction can ever cross the vast cosmic gulf. Similarly, the quantum branching of level 3 universes creates distinct, non-interacting realities. And for the abstract mathematical realms of level 4, their very nature might preclude direct empirical contact. This profound isolation means that these countless other realities remain serene, silent, and forever out of our direct reach, a testament to the vastness of the unseen cosmos. Despite this inherent unobservability, scientists are actively searching for indirect evidence, such as subtle anomalies or peculiar patterns in the E, or CMB, is the faint, pervasive glow of ancient light that fills the entire universe, a serene echo of the Big Bang. A delicate snapshot of the cosmos when it was just about 380,000 years old. This radiation is remarkably uniform, but it contains tiny temperature fluctuations that seeded the formation of all galaxies and structures. Cosmologists meticulously study these subtle variations, looking for anything that deviates from the predictions of our standard model. A peculiar pattern, an unexpected hot or cold spot, or a subtle distortion could be a gentle whisper from another reality, a faint ripple on the cosmic pond hinting at something beyond our own universe's boundaries. This patient search involves sophisticated telescopes and intricate data analysis, all in the quiet hope of finding a cosmic fingerprint. One of the most intriguing hypothetical signatures of a multiverse would be cosmic bruises, or impact sites, from hypothetical collisions between our bubble universe and another. Imagine our universe, a gentle bubble, slowly drifting through the larger metaspace of eternal inflation. It is conceivable that, at some point in its distant past, it might have gently brushed against another bubble universe. Such an interaction, though not a violent explosion, could leave a subtle, circular pattern or a distinct temperature variation in the cosmic microwave background. These bruises would be faint, almost imperceptible distortions, like soft indentations on a perfectly smooth surface. The precise shape and size of these imprints could provide clues about the properties of the colliding universe. While still highly speculative and elusive to detect, the search for these cosmic contact points represents a fascinating frontier in observational cosmology, a quest for the serene echoes of a long-past, gentle, inter-universal encounter. Among the specific features in the cosmic microwave background that have drawn attention, the cold spot is particularly compelling. This unusually large and cold region, significantly colder than its surroundings, has been speculated by some to be a possible hint of another universe's influence. While many such fluctuations are expected to arise from the random quantum processes in the early universe, the cold spot's sheer size and magnitude make it statistically anomalous, a quiet cosmic outlier. Some theories suggest that this cold spot could be the gravitational imprint of a collision with another bubble universe, or perhaps a region where our universe once touched a neighboring reality with different physical properties. While other explanations for the cold spot exist within the standard cosmological model, its persistent mystery continues to fuel speculation and inspire further research, gently nudging us to consider the possibility that it might be a subtle beacon from beyond our cosmic boundaries. Another powerful avenue for finding indirect evidence for the multiverse lies in the detection of specific patterns of gravitational waves from the earliest moments of our universe. Gravitational waves are ripples in the fabric of space-time, predicted by Einstein and recently detected by advanced observatories. The theory of cosmic inflation, which is a key mechanism for generating level 2 multiverses, predicts that a specific type of gravitational wave, known as primordial gravitational waves, would have been produced during the universe's rapid initial expansion. These waves would leave a distinctive polarization pattern in the cosmic microwave background radiation. Detecting such a pattern would provide strong support for inflationary models, and by extension, for the existence of the multiverses they predict. It would be a serene and profound confirmation, a direct link to the very processes that could have birthed not just our universe, but countless others, a cosmic whisper from the dawn of all reality. Furthermore, the search for tiny, subtle variations in fundamental constants across vast stretches of space could indirectly suggest we are part of a larger multiverse. As we've discussed, the values of constants, like the fine structure constant or the proton-to-electron mass ratio, are incredibly precise in our observable universe. However, if our universe is merely one bubble in a level 2 multiverse, where different bubbles have different constants, it is conceivable that our own bubble might not be perfectly uniform. There could be minute, almost imperceptible gradients or subtle shifts in these constants as we look across immense cosmic distances, perhaps remnants of our universe's boundary or its interaction with another. Detecting such a gentle variation would hint that our reality is not entirely isolated, but part of a grander, more diverse ensemble of realities. This meticulous scientific quest, searching for the slightest cosmic tremor, quietly pushes the boundaries of our empirical understanding, seeking any faint echo of the immense, unseen multiverse. Beyond the intricate scientific models and the elusive search for evidence, the multiverse concept invites us into a realm of profound philosophical and existential reflections, gently reshaping our most deeply held beliefs about ourselves and our place in the cosmos. Firstly, the multiverse profoundly changes our understanding of uniqueness and individuality, suggesting there are infinite versions of every person and event. If every quantum choice branches into new realities, or if infinite space repeats all possibilities, then countless versions of you exist, each a subtle variation, experiencing every conceivable path. Your successes, your failures, your joys, your sorrows, all are playing out in an endless array of parallel lives. This perspective, while initially disorienting, can also be profoundly liberating, suggesting that the pressure of a single definitive life is softened by the boundless expanse of all possibilities. It weaves a serene tapestry where every potential self finds its expression, transforming individuality into a multifaceted, infinitely recurring theme across the cosmic stage. This proliferation of selves and realities naturally raises deep philosophical questions about the meaning and purpose of life if countless iterations of our existence are playing out simultaneously. If every choice leads to a new universe, and every possible outcome is realized somewhere, does that diminish the significance of our actions in this particular reality? Or does it, conversely, amplify the wonder of each unique experience, knowing it is but one precious thread in an infinite cosmic tapestry? This question is not meant to unsettle, but to invite a gentle, contemplative introspection. It encourages us to consider whether meaning is inherent in the singular path we perceive, or if it lies in the collective symphony of all possible lives. The multiverse offers a serene backdrop against which to re-evaluate our notions of destiny, free will, and the very essence of what it means to live, gently expanding the scope of our existential inquiry. A philosophical challenge that some multiverse models encounter is known as the Boltzmann brain paradox. This paradox questions the probability of isolated consciousness arising by chance in a vast, empty universe, rather than as part of a complex, evolving system. In an infinite multiverse, where all possible configurations eventually occur, it is statistically more probable for a brain, complete with memories and sensations, to spontaneously fluctuate into existence from the vacuum for a brief moment, than for an entire, complex universe to evolve to support conscious life. This thought experiment highlights a subtle tension. If everything is possible, what prevents the most statistically easy but nonsensical possibilities from dominating? This paradox serves as a gentle reminder of the subtleties and complexities inherent in infinite systems, urging scientists to refine their models of the multiverse to ensure that the universes we actually observe, with their intricate order and sustained life, remain the most probable outcomes, preserving the serene elegance of cosmic evolution. Beyond such intricate paradoxes, the multiverse offers a compelling explanation for why our universe seems so perfectly suited for us, without needing to invoke a conscious designer. As we discussed with the fine-tuning problem, the values of our fundamental constants appear to be exquisitely balanced for the emergence of stars, galaxies, and life. In a single universe framework, this precision can seem like an almost miraculous cosmic coincidence, often leading to arguments for intelligent design. However, the multiverse provides a purely scientific, probabilistic solution. If there are countless universes, each with different physical laws and constants, then it is simply a matter of statistical inevitability that some of them will have the precise conditions necessary for life. We, as observers, naturally find ourselves in one of these life-friendly universes because we could not exist in any other. This serene explanation gently shifts the debate, offering a naturalistic account for our cosmic good fortune, rooted in the boundless diversity of existence rather than a singular, purposeful creation. This perspective also profoundly shifts the focus from a single, unique creation event of our universe to a continuous, grand process of universe generation. The Big Bang, traditionally seen as the singular beginning, becomes merely one of countless such beginnings within a larger, ongoing cosmic tapestry. Whether through eternal inflation, quantum branching, or cyclic bounces, the multiverse suggests that the universe is not a static, one-off creation, but a dynamic, ever-birthing entity. This continuous genesis paints a picture of a cosmos that is perpetually renewing itself, always expanding, always creating, always exploring new permutations of reality. It's a serene and endless cosmic dance, where creation is not an event of the distant past, but a ceaseless present, a gentle, rhythmic unfolding of infinite possibilities across the vastness of time and space. Furthermore, the concept of cosmic loneliness, the idea that we might be alone in the vast cosmos, is profoundly challenged by the notion of countless other realities. For generations, humanity has gazed at the night sky, wondering if we are unique, if our planet is the sole abode of life and consciousness. The sheer scale of our observable universe already hints at the improbability of such isolation. But with the multiverse, the possibility of life, even intelligent life, existing in other realities becomes not just probable, but almost certain. While these other intelligent beings might exist in universes causally disconnected from our own, the knowledge that they are out there, quietly living their lives in parallel realities, offers a profound sense of connection. It's a serene comfort, transforming our understanding of existence from a solitary journey to a shared, albeit separated, cosmic experience, softening the edges of cosmic isolation with the gentle embrace of infinite companionship. Ultimately, the multiverse inspires a profound sense of wonder and humility about the true nature of reality and the boundless possibilities of existence. It pushes the limits of our imagination, inviting us to contemplate scales and concepts that transcend our everyday experience. It reminds us that our universe, vast and magnificent as it is, might be but a single delicate petal on an infinitely blooming cosmic flower. This expansion of our cosmic perspective, though challenging, can be deeply soothing, fostering a quiet reverence for the intricate beauty and boundless creativity of the cosmos. It encourages us to release our rigid assumptions about what reality must be and to embrace the serene mystery of what it could be, allowing our minds to gently drift into the infinite, tranquil expanse of all possible worlds. As we continue our serene journey through the intricate concepts of the multiverse, we encounter several related theoretical frameworks that further deepen our understanding of reality's potential. One such profound idea is the holographic principle, which suggests our three-dimensional universe might be a projection from a two-dimensional surface. Imagine a hologram where a three-dimensional image is encoded on a two-dimensional film. The holographic principle, especially prominent in theories involving black holes and string theory, proposes that all the information contained within our expansive three-dimensional cosmos could actually be encoded on a distant, two-dimensional boundary. This means that our perceived reality, with its depth and volume, might be an elaborate illusion, a gentle cosmic projection. Extending this to the multiverse, one can then contemplate a holographic multiverse, where countless three-dimensional universes are projected from various two-dimensional surfaces, creating an even more intricate and layered cosmic tapestry. This idea elegantly redefines the very nature of space and information, suggesting a subtle, almost ethereal foundation for all existence, further hinting at deeper connections within reality, quantum entanglement, where particles remain linked across vast distances, could also be related to multiverse structures. Quantum entanglement is one of the most mysterious phenomena in physics, where two or more particles become intrinsically linked, sharing a common fate regardless of the distance separating them. A change to one instantly affects the other, as if they are communicating faster than light, though no information is actually transmitted. This profound interconnectedness, defying classical intuition, might be a subtle whisper from a larger, more unified reality. Some theories gently propose that this entanglement could be a direct consequence of the universe branching in the many worlds interpretation, or that it hints at a deeper, underlying structure that connects seemingly disparate realities within a broader multiverse. The serene and instantaneous correlation between entangled particles suggests a cosmic unity that transcends our immediate perception, subtly weaving together the fabric of existence across potential multiversal dimensions. However, as we explore these boundless possibilities, a significant challenge arises known as the measure problem in cosmology. This problem attempts to define probabilities for different outcomes in an infinite ensemble of universes. If an infinite number of universes exist, and every possible event occurs an infinite number of times, how do we assign a probability to any particular outcome? For example, in a level 1 multiverse where identical copies of you exist infinitely, what is the probability that you are in this particular copy? Or, in eternal inflation, how do we compare the likelihood of different types of bubble universes forming without a consistent way to measure or weight the probabilities of different events or universes? Making predictions from multiverse theories becomes exceedingly difficult. This measure problem is a gentle but persistent puzzle, challenging cosmologists to develop elegant mathematical tools to navigate the boundless landscape of probabilities, ensuring that our understanding of the multiverse remains grounded in rigorous scientific reasoning. Another intriguing concept, cosmic natural selection, proposes that universes capable of reproducing, for example, by spawning black holes, would be more common in a multiverse. This idea, sometimes called fecund universes, suggests an evolutionary process at the cosmic scale. Universes that are particularly adept at creating black holes, which some theories link to the birth of new universes, would effectively reproduce more successfully. Over countless cycles within the multiverse, these fecund universes would become more prevalent, subtly shaping the overall landscape of cosmic properties. This means that the physical laws and constants we observe in our universe might not just be fine-tuned by chance, but might be the result of an evolutionary pressure favoring universes that are good at spawning offspring. It's a serene and grand vision of cosmic evolution, where entire universes undergo a gentle form of selection, favoring those that are most prolific in their generation of new realities. Directly related to this, the baby universe theory suggests that black holes, through their singularities, might act as gateways or progenitors for new, distinct universes. Instead of ending in a destructive singularity, the extreme conditions within a black hole's core could, in this theoretical framework, provide the necessary environment for a new universe to bud off, might contribute to the formation of a nascent universe, expanding on the other side of the singularity, completely disconnected and unobservable from our own. This elegant concept transforms black holes from mere cosmic devourers into subtle cosmic nurseries, perpetually giving birth to new realities. Each black hole, then, becomes a potential seed for a new cosmos, quietly expanding the multiversal tapestry through a continuous, unhurried process of creation, a gentle and mysterious link between the vastness of space and the origins of new worlds. The existence of a multiverse also provides a profound context for understanding our own physical laws. The standard model of particle physics, with its many specific parameters and forces, could represent just one particular outcome chosen from the vast multiverse landscape. Our universe is governed by a precise set of fundamental particles and forces, each with specific properties and interaction strengths. These are the rules that allow for atoms, molecules, and all complex structures to exist. However, in a multiverse where different universes possess different laws and constants, our standard model is simply one of countless possible configurations. It is the specific recipe that happened to manifest in our particular cosmic bubble, allowing for the evolution of observers like us. This perspective offers a serene and humble understanding of our physical laws, seeing them not as uniquely ordained, but as one beautiful variation within an immense, boundless ensemble of cosmic possibilities. Ultimately, the multiverse concept helps to address the fundamental "why this universe?" question in cosmology by offering a broader context for its existence. Without the multiverse, the remarkable fine-tuning of our universe, its initial conditions, and the very laws that govern it can seem arbitrary or even miraculous. It compels us to ask why this specific set of parameters, out of an infinite number of possibilities, was chosen. The multiverse gently resolves this by suggesting that no choice was made. Instead, all possible universes exist, and we naturally find ourselves in the one that supports our existence. Our universe is not unique in its perfection, but merely one of the many that possess the right conditions. This perspective provides a serene and probabilistic framework, transforming the question of cosmic purpose into one of statistical inevitability within an infinitely diverse cosmic ensemble, allowing us to contemplate our existence within a grander, more logical narrative. As we gently approach the outer edges of our exploration into the multiverse, it is important to recognize that this profound concept is far from a mere flight of fancy. The multiverse theory is an active and dynamic area of research in theoretical physics, extending far beyond the realm of science fiction. While it captures the imagination, its roots are firmly planted in the mathematical consistency and predictive power of modern cosmological and quantum theories. Leading physicists and cosmologists around the world are dedicating their careers to exploring its implications, developing rigorous models, and searching for subtle, indirect evidence. This scientific pursuit is driven by deep questions that the single universe model struggles to answer, such as the fine-tuning of cosmic constants and the nature of quantum reality. It is a quiet, persistent quest for a more complete understanding of existence, pushing the boundaries of our knowledge with serene determination. Indeed, the multiverse theory provides a grand framework that attempts to connect quantum mechanics, general relativity, and particle physics in a more unified understanding of reality. For decades, physicists have sought a theory of everything that harmoniously integrates these fundamental pillars of modern science. General relativity beautifully describes gravity and the large-scale structure of the cosmos, while quantum mechanics precisely governs the subatomic world. Particle physics details the fundamental building blocks and forces. Yet, these theories often clash when applied to extreme conditions, such as the very early universe or the interior of black holes. Multiverse models, particularly those arising from string theory and inflationary cosmology, offer a serene landscape where these disparate theories might naturally converge, providing a broader context for their individual truths. It's a gentle effort to weave together the intricate threads of cosmic understanding, creating a more cohesive and elegant picture of how the universe, or rather, universes, operate. In the quest for subtle clues, future generations of gravitational wave detectors might potentially provide indirect hints about the violent early universe phase, transitions linked to multiverse creation. Gravitational waves, ripples in the fabric of space-time, are powerful messengers from the most energetic events in the cosmos. While current detectors are sensitive to massive black hole mergers, future observatories aim to detect the faint, primordial gravitational waves predicted to have been generated during cosmic inflation, just moments after the Big Bang. These waves would carry a unique signature, a specific pattern of polarization, not only confirm the theory of inflation, but also offer profound insights into the extreme conditions that could have given rise to an eternally inflating multiverse. It would be a serene and delicate whisper from the dawn of time, a subtle vibration in the cosmic fabric, offering a rare glimpse into the very birthing processes of realities. To explore the vast and complex landscape of potential universes, advanced computational simulations are increasingly being used to model the potential dynamics, properties, and interactions within various multiverse scenarios. Since direct observation is often impossible, supercomputers become essential tools for theoretical physicists. These powerful simulations allow researchers to create virtual universes, varying their initial conditions, physical constants, or inflationary parameters, and then observing how they evolve over cosmic timescales. By running countless iterations, scientists can explore the statistical likelihoods of different types of universes emerging, study hypothetical collisions between bubble universes, or model the intricate branching processes of quantum realities. This computational exploration offers a serene and systematic way to test the consistency of multiverse models, allowing us to visualize and analyze scenarios that are otherwise beyond our direct perception, gently expanding our understanding through digital cosmic creation. However, the very nature of the multiverse concept challenges the traditional limits of empirical science due to the inherent unobservability of other universes, pushing the boundaries of scientific inquiry. The cornerstone of scientific method is testability. A theory must make predictions that can be verified or falsified through experiment or observation. Since most multiverse models posit realities that are fundamentally inaccessible to us, they present a unique methodological dilemma. How can we prove something we can never directly see or interact with? This quiet challenge encourages scientists to rethink what constitutes evidence in cosmology, leading to a focus on indirect signatures, mathematical elegance, and the ability to solve existing puzzles more coherently. It invites a gentle re-evaluation of the scientific process itself, acknowledging that some of the grandest truths about reality might require a broader, more nuanced approach to verification. By embracing this challenge, the multiverse concept encourages scientists and thinkers to conceive of reality beyond our observable cosmic horizon, expanding the scope of cosmological thought. For centuries, our view of the universe has been limited to what we can see, a finite sphere of light and matter. The multiverse gently breaks these conceptual chains, inviting us to imagine an existence that is vastly larger, more diverse, and more dynamic than we ever thought possible. It prompts profound questions about the nature of space, time, causality, and identity, inspiring new avenues of theoretical exploration. This expansion of thought is not merely intellectual. It is a serene and awe-inspiring invitation to envision a cosmos of boundless creativity, where our familiar reality is but intricate whole. It fosters a quiet sense of liberation, allowing our minds to wander into truly limitless possibilities. Finally, the study of dark energy and its consistency across the observable universe is highly relevant to multiverse models, as it represents a finely tuned cosmic parameter. Dark energy, the mysterious force driving the accelerating expansion of our universe, constitutes nearly 70% of its total energy content. Its measured value is incredibly small and precise, another example of cosmic fine-tuning. If its strength were even slightly different, our universe would either have expanded too rapidly for structures to form, or it would have collapsed long ago. Cosmologists are diligently studying whether the properties of dark energy appear perfectly uniform throughout our observable universe. Any subtle variation or anomaly could provide a crucial clue. In the context of a multiverse, where different universes have different values for dark energy, our specific value is simply the one that allowed for our existence. This ongoing investigation into dark energy's nature is a serene and critical frontier, potentially revealing subtle echoes of a larger cosmic ensemble, weaving our universe into the grand tapestry of multiversal possibilities. As our tranquil journey through the intricate layers of the multiverse draws to a close, we are left with a profound sense of wonder and an enduring appreciation for the ceaseless pursuit of cosmic understanding. It is important to remember that the multiverse concept is constantly evolving, with new theoretical developments, interpretations, and refined mathematical models emerging from ongoing research. This is not a static idea, but a vibrant and dynamic field where scientists are perpetually refining their understanding, gently pushing the boundaries of what we thought possible. Each year brings new insights from string theory, quantum gravity, and inflationary cosmology, contributing fresh perspectives and more sophisticated frameworks to describe these potential realities. The quiet, persistent work of theoretical physicists continues to sculpt and reshape our understanding, building a more nuanced and elegant picture of the cosmos, a testament to the ever-unfolding nature of scientific discovery. While the multiverse theory offers potential solutions to some of the deepest puzzles in cosmology, it also introduces new, complex questions and challenges to our understanding. It gracefully addresses the fine-tuning problem, for instance, by providing a probabilistic framework for our existence. However, in doing so, it opens doors to new enigmas, such as the measure problem, which seeks to define probabilities within an infinite ensemble of universes. It challenges our notions of empirical verification, given the inherent unobservability of other realities, and prompts us to reconsider the very nature of scientific proof. These new questions are not roadblocks, but rather gentle invitations to deeper thought, encouraging further exploration and innovation in our scientific methodologies. The multiverse, in its serene complexity, enriches the cosmic narrative, transforming our understanding from a simple tale into a grand, multi-layered epic. Regardless of its ultimate scientific verification, the multiverse theory profoundly expands our imagination about what reality could truly be, fostering boundless curiosity. Even if direct evidence remains elusive, the mere contemplation of parallel universes, infinite possibilities, and varying physical laws stretches the very limits of human thought. It encourages us to look beyond the confines of our observable cosmos and to imagine worlds where dinosaurs still roam, where time flows backward, or where entirely different forms of matter exist. This imaginative expansion is a deeply soothing and inspiring experience, reminding us that the universe is far stranger and more magnificent than our everyday perceptions might suggest. It cultivates a quiet reverence for the unknown, inspiring future generations to continue gazing upward and inward, seeking to unravel the boundless mysteries that lie within and beyond our reach. In the gentle quiet of this cosmic contemplation, the ultimate truth about the existence and nature of the multiverse remains one of the greatest scientific mysteries, patiently awaiting future revelations and discoveries. We stand at the precipice of understanding, with powerful theories and subtle hints, but without definitive proof. The journey to unravel this enigma is long and unhurried, requiring continued intellectual rigor, technological advancement, and an open, curious mind. Future generations of scientists, armed with new instruments and deeper insights, may one day find the conclusive evidence that gently lifts the veil from these hidden realities. Until then, the multiverse remains a profound and beautiful possibility. A tranquil whisper from the edge of knowledge, inviting us to rest in the boundless potential of a cosmos that is ever expanding, ever creating, and eternally mysterious. As the profound questions of the multiverse gently recede, allow your thoughts to drift away from the vastness of infinite realities. Now, the stars continue their serene dance across the endless night, each a distant sun, quietly burning and nurturing its own potential worlds. Galaxies, immense islands of light and dust, drift in silent harmony, their spiral arms slowly turning through the cosmic dark. Light from distant worlds, traveling for countless eons, washes over us, a gentle cascade of ancient information. You are a part of this vast unfolding story. The atoms within your very being were forged in the hearts of ancient stars, scattered across the cosmos, and then patiently reassembled to form you. You are woven into the very fabric of this grand cosmic tapestry, connected to the quiet birth of nebulae and the slow, majestic evolution of galaxies. In this moment, as you rest, the universe continues its gentle work. New stars are forming in distant clouds, light is traveling across unimaginable gulfs, and the cosmic dance carries on, serene and eternal. May your rest be peaceful, and your dreams be filled with the quiet wonder of the cosmos. Good night.